Hi all, today we start discussing section 14.8. This is the last section of our module 2. Uh, in 14.8 we will discuss a new method to evaluate the extreme values of a function using some constraints. So that is the idea in this section. We explain a couple of problems first, then we will introduce a new method. First, find the point P of xyz closest to the origin on the plane qx plus y minus z minus 5 equal to 0. That means the this, the closest point of the plane, okay, or the point in the plane whose distance is minimum to this origin. Okay, so the problem asks to find the minimum value of the function OP. Okay, that is if we consider a plane right here, and suppose we have uh, origin here, and we need to find out P such that this OP is minimum. Okay, so in order to find out that point P, we first define a function OP. Okay, if P is the point XYZ, then OP gives the length of the OP gives root of x square plus y square plus z square. We need to find out P such that this distance is minimum, and with the condition that this P should lie on the plane 2x plus y minus z minus 5 equal to 0. So in order to minimize this quantity, it is enough to minimize x square plus y square plus z square. Okay, the minimum value of x square plus y square plus z square attains at x, y, z, and we can say that the minimum value of this quantity is also attains the minimum at this point. Okay, because if we consider the point x, y, z, then this root x square plus y square plus z square and square of this root of x square plus y square plus z square whole square, that gives this quantity. So this is a squaring is a increasing function. Whenever this value increases, then square increases. Okay, so that means a less than b, then a square is less than b square. Okay, so this is the idea here. That is, whenever a less than b implies a square less than b square. That means if all these quantities are greater than 0, that's one thing you should remember. For positive quantities, these things are true. Therefore, in order to minimize this quantity, it is enough to minimize this, or vice versa. In order to minimize this a, you consider the smallest a square among those numbers. So, in order to minimize this quantity, we need to minimize x square plus y square plus z square. So for that we set f of xyz as x square plus y square plus z square, and we need to minimize this quantity according to this 2x plus y minus z minus 5 equal to 0. For this, the one way of doing this is we write z equal to, from this equation, write z equal to 2x plus y minus 5 and substitute this z in this expression. Okay, that means this gives set of all x, y, z with this condition gives the plane. So we need to work out, consider all the points on the plane whose distance is minimum. So we substitute this is the arbitrary point of the plane, and for this z we can write 2x plus y minus 5. So in order to get the distance, you need to replace this z by this quantity 2x plus y minus z y minus 5. Then the new function f of x, y, z can be reduced to a function of x and y alone. That means that is denoted by h of xy, that is equal to f of xy comma 2x plus y minus 5. So that will give this expression. So we need to find out the minimum value of the points at which this value is minimum. So we use the argument of the or first the second derivative, first derivative results for getting the minimum value. For that we write hx and xy first. The partial derivative of this function with respect to x, that will give the derivative of x square, that is 2x, derivative of y square, that is 0, and derivative of this quantity. for the derivative of this quantity, we need to use the chain rule, that is 2 times 2x plus y minus 5, and the derivative of this expression with respect to x, so that will give 2. So this is hx. We need to equate this hx to 0 in order to get the extreme values. Similarly, evaluate hy, that will give this expression, and equate it to 0. From these two equations, you can get system of two linear equations: 10x plus 4y equal to 20, 4x plus 4y equal to 10. When subtract these two, you can get 6x plus 0 equal to 10. Then x equal to 10 by 6, equivalently x equal to 5 by 3, and substitute this to one equation, you can get y is equal to 5 by 6. So these are the points at which this hx and hy equal to 0. So now we find out a point z which satisfies this condition. So first you evaluate, you can get the point takes the form 5 by 3 and 5 by 6 and z. So this is the form of the points for which the distance is minimum. We need to, our requirement is this point should lie on this plane. Okay, so we need to find out z which satisfies this condition. So we solve for z. So z is obtained by 2 times x is 5 by 3 plus y is 5 by 6 minus 5 equal to minus 5 by 6. When you simplify this, you can get minus 5 by 6. So we can say that the required point is, or extreme value of this h of xy attains at the point 5 by 3, 5 by 6, and the corresponding point in the plane is minus 5 by 6 as well. So in order to get the behavior of this point 5 by 3 and 5 by 6, we didn't verify that this is maximum or minimum. In order to verify this is maximum or minimum, we need to use the second derivative test, that is find out hxx. Okay, that is 10 here, the derivative of this expression with respect to x. Derivative of 2x is 2, derivative of this is 8x, 8x is 8, then 8 plus 2, that is 10, and rest of them are 0. Similarly, hyy, that is obtained from this expression by differentiating this expression with respect to y. So from this you can write the derivative of this with respect to x is with respect to y is 2 plus derivative of 2y, that is again 2, so that will give 4. Okay, and hxy, so this can be obtained from one of these equations by differentiating with respect to y, differentiating hx with respect to y. So when you differentiate this with respect to y, you can get this as 4y and derivative is 4. Now you evaluate hxx, hyy minus hxy whole square. So that is 40 minus 16, that is again 40 minus 16, that is 24, that is always greater than 0. Therefore this by looking into the sign of this hxx, you can say that this is point of maximum or minimum. Since this is greater than 0, the point 5 by 3 and 5 by 6 is a point of minimum. So this hxy is the minimum value. So in order to get that minimum value, we evaluate our function. Our required function is this one rather than this. Okay, so this is the point at which this is minimum. Okay, so in a similar way we can say that this is the point at which this quantity is also minimum because of this fact. Whenever a square is less than b square, then a is less than b. Yeah, so you evaluate the function at this point 5 by 3, 5 by 6 minus 5 by 6. When you evaluate this, you can get the value as square root of 5 by 3 whole square, that is 25 by 9 plus again 25 by 36 plus 25 by 36 again. So this can be written as, you can take this 25 out, then this 5 can be taken out from the square root, and the rest of them are this is 1 by 9 plus 1 by 36 and again 1 by 36. When you multiply it with 4, then you can get this is 4 by 36. So this will be, the total sum will be 6 by 36, that is 1 by 6, root of 1 by 6. So this will give 5 by root 6, that is approximately 2.04. So this is the minimum value. So this is the lengthiest procedure to evaluate the minimum value with respect to some constraint. Okay, in this section we will discuss how find out the minimum value of function with constraints in easier method. Okay, so next we will explain one more illustrative example at which this process is a little bit complicated. So next we will consider example 2, the closest point to the origin from the hyperbolic cylinder x square minus z square minus 1 equal to 0. This is a hyperbolic cylinder. This is the figure. This can be easily identified using this argument: x square minus y square is equal to 1. That is this parabola, this hyperboloid, and that is a cylinder corresponding to that. Okay, so when you extend this blue hyperbola along this way and this along this way, you can get this cylinder. Okay, this is what we call the hyperbolic cylinder. Okay? So we need to find out the closest point of the cylinder to origin. So the general procedure is evaluate the distance function. In fact, this distance function is square root of x square plus y square plus z square. In order to minimize that distance, it is enough to minimize this function x square plus y square plus z square. Okay, but the minimum distance is square root of this anyway. Yeah. Then for that we substitute for z in this expression. So z can be obtained from the equation of the cylinder, that is z square. This is hyperbolic cylinder, not the usual cylinder. The usual cylinder is obtained by taking a circle and extend it along the axis of z axis. Similarly, if you take a hyperbola and extend it in this way, you can get the hyperbolic cylinder. Okay, so this is what we have seen in this figure. Then consider this equation: x square minus y square minus x square minus z square minus 1 equal to 0. From this z square, from this expression, find z square and substitute for z square in the expression of f of x, y, z. So that will give a new function in x and y, that is x square plus y square plus x square minus 1. So this is what we call z square. So by simplifying this, we can get a new function h of xy. Our next intention is to minimize this h of xy and find out the point of extreme of this xy which corresponds to a point in this cylinder. That is our requirement. For that we consider this expression and hx and hy. But here we have x equal to 0 and y equal to 0 by equating this hx and hy to 0. Then we need to find out the corresponding point in the hyperbolic cylinder. But no point of this form lie in this expression. Whenever x equal to 0, we can say that z square equal to minus 1 from this. Okay, x equal to 0, we can get minus z square is equal to minus z square equal to minus z square equal to 1. That implies z square equal to minus 1. This shows that no point satisfying this condition lie on that hyperbolic cylinder. Okay, so if you evaluate this to get the point of extrema, so that point doesn't lie on the cylinder. That means whenever x equals 0 and y equals 0, then no point on that cylinder attains the minimum with these criteria. Okay, so this is because when you consider these points, we are considering only this part. Okay, by substituting this z square equal to x square minus 1 in this expression, and this gives only the points of the plane. Okay, even though the domain of h of xy is equal, xy is the whole R2 plane, we can say that in order to satisfy this condition, we need to set x equal to 0 and y equal to 0. If you set this x equal to 0, y equal to 0, we can never get a point on the corresponding cylinder. Clear. So the one way of rectifying this is considering instead of z square we will substitute for x square in this expression. Okay, we are not dealing with x and y are independent variable. We will consider y and z are independent variable. Okay, then for that we substitute for x square. Okay, so when you substitute for this x square, we can get f of x y z as a function of y and z alone. Now apply the same things. We call that function as k of yz. So ky and kz, that is partial derivative of k with respect to y and partial derivative of k with respect to z. That will give y equal to 0 and z equal to 0. This is another possibility. Now find out a point satisfying y equal to 0 and z equal to 0 in this plane, this hyperbolic cylinder. Okay, so with this condition we can extract a point from this. Okay, when you put z equal to 0, or in this expression when you put z equal to 0, you can get x square is equal to, so this implies x square is equal to 1. That implies x is equal to plus or minus 1. Now you can get 2.100 and minus 100. These are 2 points on the hyperbolic cylinder. Okay, so this expression or this function would enable us to get 2 points from the cylinder which minimize this x square plus y square plus z square. Yeah. Now you find out these 2 points. So what is the minimum value of this k of yz with these points? So in order to get that, we write. We can easily find out that quantity because of the simplicity of this expression. We know that when you consider k yz, that function is 1 plus y square plus 2z square. This is always greater than or equal to 1, because this quantity is always greater than 0, greater than or equal to 0 because of this square factors. Then we can say that this expression is always greater than or equal to 1. So the minimal the least possible value of this quantity is 1. But we know that whenever x equal to 1 or x equal to minus 1, then you can get this k of yz, or x equal to minus 1 and 0 0. At this point, at these 2 points, this kyz attains the value 1. So we can easily say that this, the minimum value of this expression is 1, and it attains at the point 100 minus 100, and both of these points are lying in this hyperbolic cylinder. Okay, and we can say that the distance between this point and 0 0 0, and a distance between these 2 points and distance between these 2 points, that are always 1. So you can say that the minimum distance is 1. Okay, so this is one way of doing this. Another interesting idea is this is the another method of finding the minimum value. In order to find out the minimum distance, we consider this a small sphere like this, and try to enlarge this cylinder with its radius. Okay, and find out the cylinder which touches this hyperbolic cylinder. Okay, so consider the spheres with radius, arbitrary radius and arbitrary small radius, and enlarge this sphere with its radius, and find out the sphere for which the sphere touches this hyperbolic cylinder. So in order to use that idea, we consider a function. This is the whenever this is equal to 0, you can get the sphere of radius a. Okay, and the corresponding function, the corresponding hyperbolic cylinder, and you construct a function del f equal to lambda times del g. This del f is the gradient of f. Okay, this del f is defined to be dou f by dou x, dou f by dy, and this is the partial derivative of f with respect to x, partial derivative of f with respect to y, and the partial derivative of f with respect to z, and del g gives the partial derivative of g with respect to x, partial derivative of g with respect to y, and partial derivative of g with respect to z. Okay, when you evaluate this quantity and equate this. Okay, so the idea is when you enlarge this quantity, this sphere touches this hyperbolic cylinder. At the point the sphere touches this hyperbolic cylinder, then the normal at this point will be in the same direction. That is idea. Okay, so the normal of this sphere is exactly the same as or that is in the direction of normal of the hyperbolic cylinder. So the normal is obtained or can be evaluated using del f and this del f for this sphere and del g for this hyperbolic cylinder. So the idea is when you find the situation when you find the case where, at which this sphere touches this hyperbolic cylinder, the normal at this point, the point of intersection of sphere and this hyperbolic cylinder is in the same direction. That means del f and del g is in the same direction. Same direction means in one line. Okay, so we can assume this del f is lambda times a constant multiple times del g. Okay, the del f and del g will give the normal at this point. Okay, so that is the idea here. We will extend this idea to the theorem, Lagrange multiplier theorem. We will see later. So if you solve this, you can get two equations. That is 2x equal to 2 lambda x, 2y equal to 0, or 2z equal to minus 2 lambda z. Okay, we will find out x, y, z from this expression. Okay, and we will substitute it in the equation x square minus y square. We know that x square minus z square minus 1 equal to 0 for the hyperbolic cylinder. So we need to collect the points from those surfaces. Okay, so when you substitute these equations in this equation and solve for x, so you can get solve for lambda, so you can get 2x equal to 2 lambda x. Okay, so this holds only if 2 is equal to 2 times lambda or lambda is equal to 1. Okay, or using this equation and this solve the value of lambda. If lambda is equal to 1, that defines the points x, y, and z. Okay, so when lambda equal to 1, you can get 2z is equal to minus 2z. Okay, from this you can write as z equal to 2z equal to minus 2z. That is 4z equal to 0. That is z equal to 0. Okay, z equal to 0, and from this you can easily get y is also 0. So z equal to 0 and y equal to 0. Okay, and x is an arbitrary quantity. X cannot be when lambda is equal to 1, you can get 2x equal to 2x. You cannot find the value of x. So we will say that this is the point at which this expression or f of x, y, z is or del f is in the direction of del g. Okay, so in order to find out this point in this hyperbolic cylinder, we substitute this value in this equation, and we can get x square minus 0 square, because z is 0, that is equal to 1, then x square equal to 1, then x equal to plus or minus 1. So this is another way of doing the same problem. So these are not the simplest way. We will later we will explain how we simply how we reduce these process to evaluate the point of extrema using constraints. Okay, so that we will discuss in the next class.